And the next speaker is Lüst, who's going to talk about two subjects that at first sight have nothing to do with each other, namely duality and strings.
So it's indeed my real big pleasure and honor to be here to talk at this very nice event to honor Louis and his 60th birthday and his very nice achievement. So thank you very much for the invitation. The title is Duality and Strings, and Bert was saying duality has nothing to do with strings. Let's see whether it's true or not. We don't know really yet, but I think I will also use the notion of duality in a bit broader sense, as we will see now. I think everybody knows here that Louis made several very profound and important contributions to theoretical physics, so I do not dare to name them all. But what I like, of course, to emphasize is that we were often working on related subjects, and moreover, and this is very nice and important to me, I enjoyed various very nice collaborations and good friendship with Louis. So I also, like Anna-Maria, start a little bit in the past, so mentioning a few things which were done now first in the 80s. And the 80s and 90s, in some senses, were still the golden days, I think, of string compactifications and, of course, duality symmetries. And it was very nice to be also at CERN at that time and to work with Louis. So, for example, there's a duality of four-dimensional string constructions, covariant lattices, and orbifolds. Covariant lattices were done by us in collaboration with our chairman, Bert Schelikens, and Louis, Hans-Peter, and Fernando did very important and nice work on orbifold constructions. And basically, one can say this story repeated in about 13 or 14 years later, where again we worked on certain string constructions which are called intersecting brane or intersecting d-brane models. And so there are these very nice papers by the people here in Madrid, and it sounds almost like a disease, but I think it isn't. There's a so-called Madrid or Spanish quiver, so it's not a certain kind of flu or influenza. It's something really very nice, which one uses to model the standard model fields living on d-brane intersections. So one can say there's really a duality of burning common interest in many respects. But also the more concrete scientific duality has played always an important role, in particular also in our common work. So let me very briefly remind you what duality in string theory and string compactification means. It relates different geometries, for example, large and small backgrounds. This is called T-duality. It is really a stringy symmetry. One needs momentum and winding mode, so one can combine the momenta and the winding into a larger two-dimensional or 2D-dimensional vector. This will be convenient also later on. This also suggests the doubling of space-time or space coordinates, which already was introduced by Gerardo. It's called doubled geometry. So this would be the ordinary coordinates, and these are the dual coordinates, dual to the winding momenta. And duality also then not only arises in the context of string compactifications as a geometric symmetry, but it relates also strong and weak coupling in string theory, and there it is called S-duality. And later I will also show you that it relates conventional Riemannian geometries to new stringy geometries, kind of non-geometric flux compactifications, which Al-Zabal also introduced already this morning. And I like to add a little bit more to this story, namely there's a very nice, I think, non-commutative or even non-associative twist in this story. But before I come to it, I hope you forgive me if I show a few of our common papers with Louis, which were really very much fun to write at that time together. I think I have 7 papers with Louis, so let me show, I think, 3 of them. Namely, first we had this paper, and not only with Louis, but also with Anna-Maria and Fernando, and we are all here together. So this was supersymmetry breaking from duality invariant Gaugino condensation. And I just summarize very briefly what we did in these papers to recollect it. Of course, the authors will remember it, but probably not everybody else. In this paper, we considered the so-called T-duality invariant non-perturbative superpotentials, which arise from Gaugino condensation in the four-dimensional effective action. And therefore, the superpotential in terms of this T modulus, which is basically the radius of the compactification, is given in terms of this modular function, Dedekind function. And this has very nice properties. It leads to spontaneous supersymmetry breaking, and also I think this was one of the first examples also of stabilization of this modulus. So the T field was fixed at some particular value, and this has to do with the modular properties of this effective action. And one should also, of course, then mention that at the same time there were also papers by Hans Peter and Olechowski and Ferrara et al., which basically came to the same conclusion. Okay, so this was one paper I like to mention. The next one is about S-duality, strong decoupling duality and non-perturbative effects in string theory. Again, this bunch of 4 people. And very briefly, I again like to summarize this paper. I think it's fair to say that we conjectured, probably for the first time at least in string theory, here the emergence of S-duality as a strong weak coupling symmetry in the context of the compactified heterotic string. And since this conjecture was kind of bold at the time, we gave a few kinds of motivations or argument why it should be or why it could be true. Namely, Olive and Monton electric magnetic duality was of course known, so we tried to generalize this to the heterotic string. We also thought that the elementary string must be dual to the wrapped NS5 brane duality if you go to 4 dimensions. So this is another, I think, strong motivation for the S-duality. And then we also basically speculated about a geometric emergence of S-duality, namely from the compactified 11-dimensional supergravity. M theory was not known at that time, but 11-dimensional supergravity was certainly known. And we speculated that the heterotic string can be obtained from an 11-dimensional membrane, which is compactified down to 10 dimensions. And this then was made much more concrete a few years later by Horava and Witten. And basically, our idea was also, like the T-duality invariant action, we wanted to write down an S-duality invariant action, which we then also investigated. Okay, so here we are. This picture is not from these days. I think it was made 1.5 years ago here during the inauguration of this very beautiful center in December 2011. Okay. Finally, I also want to very briefly mention this work, which was done with Lüst together about duality anomaly cancellation and string unification. There was a precursor paper also together with Graham Ross, where we also looked at string unification and duality symmetries. And here we obtained some kind of unexpected stringy constraints on the massless particle spectrum in compactified string theory from the requirement of absence of so-called sigma model or duality anomaly. So in a field theory, you would not guess these kind of restrictions, but in string theory, they arise. And then in the second part, we also provided a model-independent discussion of the soft parameters in heterotic string compactifications after some generic supersymmetry breaking mechanisms. So this was really fun work, and I just wanted to recollect a few of these things today. So the further outline now of my talk, and now we come to today, I want to speak about non-geometric flux compactifications and non-commutative and non-associative geometries. This is joint work with a various number of people in Munich. And we had also last week a paper with my student Falk Hassler, which is called Intersecting Q and R branes. So maybe I have time to talk also a little bit about it, and then very briefly I come also to the future, like Anna Maria, to the outlook and to the open problems. So let me very briefly summarize what are non-geometric flux compactifications, and I do it by confronting them before to what you know very well, namely to standard Riemannian geometry. Here are a few very simple examples of manifolds of Riemannian spaces, which you all know. And when you go to your math course, what is the definition of a manifold? A manifold in general needs different coordinate charts, which are patched together by coordinate, or maybe say better, diffeomorphism transformation. So normally, which you know it's true already for a sphere, it's not enough to have one coordinate patched, you need two, and you have to patch them together by diffeomorphisms. So transformations F which go from one patch U to another patch U prime. Properties of Riemannian manifolds is that distances between points can be arbitrarily short, coordinates commute with each other, and this is basically the situation if one using point particles to probe distance in the geometry of space. However, strings are not point-like, they are extended objects, and therefore one might wonder whether the notion of geometry can be, or the notion of manifolds can be generalized if one is using extended closed strings to probe space. And I want to now argue that they see some generalization which also people often call non-geometry. Maybe it's not a very good phrase, non-geometry. It's also a certain kind of geometry, but it goes definitely beyond Riemannian geometry. And these are non-geometric backgrounds pioneered by several people, not to annoy Louis on his celebration day. I put his name here in red. He also worked on non-geometric flux compactification several years ago. I will probably also mention this once again. And to be more specific, there are certain type of non-geometric backgrounds. And I will discuss those which nowadays are called Q fluxes and R fluxes. So first, the Q fluxes, these are spaces which are locally still Riemannian manifolds, but not anymore globally. So there's a global obstruction for them being manifolds. And the global obstruction is as follows. Now we generalize the concept of diffeomorphisms in the following way, that the transition functions of two coordinate patches are now given by T-duality transformations. And this is allowed in string theory because T-duality is a good symmetry in string theory. So you can even patch together a small space of radius r together with a large space of radius 1 over r, and vice versa. And this is still an allowed operation. In a little bit more general, these are the so-called OD, D transformations which exchange the coordinates by the dual coordinates. Now, as I will argue in a moment, it is precisely this Q space which will become non-commutative by some interesting reason. So if you have such a space, some of its coordinates will not commute anymore. There is an even more drastic non-geometric background which is called R fluxes. They are more mysterious and a little bit less well understood. And these are spaces which are even locally not anymore manifolds. So it's even, I think, a little bit difficult to speak about points on them, but we can still try to do it. And the argument will be here that the R space will become non-associative. So instead of a commutator, you can define a certain so-called 3 bracket, which is basically a double commutator plus all its cyclic commutations. Basically, it's the Jacobi identity of the commutator. And in case this object is non-zero, you can see immediately that associativity is lost, because if you write it if you write down all the individual terms, you will see the multiplication now depends on the order, and therefore, if the right-hand side is non-zero, there is non-associativity. So let me give you some examples, some toy models first. And the toy example, which I will discuss, is a 3-dimensional space which has the form of a 1-dimensional circle over which a fibered two torus is living. The circle coordinates are denoted by x3, and the fiber coordinates are denoted by x1 and x2. And now, as I have already indicated on the last slide, the global property or the vibration is specified by the so-called monodromy property. Namely, you ask the following question: what is happening with the torus upstairs if I transport it around the base several times? So, and I can phrase this in the following way. I can introduce a certain background parameter of the two torus, which is just the sum of the metric of the two torus and this antisymmetric tensor field, which lives in this two-dimensional space. And these parameters in general now depend on x3. They are not anymore constant. And now I'm asking what is happening if I go from x3 to x3 plus 2 pi. And then string theory tells me that I can do an OD, O2,2 transformation on these backgrounds for patching it together. This is a so-called O2,2 monodromy. And I can phrase it also in the following way. I can introduce a complex structure tau and the scalar parameter rho of the two torus. And now I'm asking myself, what is happening again with this tau and rho if I go from x3 to x3 plus 2 pi? And string theory tells me that on both of these parameters I can do SL2 transformations, similar as we did it also in the old work about the T-duality effective action. And these are allowed operations which I can use now to define my space. Okay, this can be best even more made concretely by a chain of 4 T-dual examples. So I can start with a geometric space, which is a flat three-dimensional torus with a so-called H-flux. An H-flux, constant H-flux you get if you choose a linear B field. So the B field in the upper block depends on x3 in a linear way. So the rho has this particular form, and the monodromy is simply now the shift in the B field when you go around. So if you shift x3 by 2 pi times r3, the rho undergoes this transformation, and this is particular element of O2,2. Now I do a T-duality in x1, and then what is going to happen is that this space with an H-flux becomes a completely geometric space, namely a so-called twisted three torus or a nil manifold with F-flux. And here you see the B field is T-dualized array. The two-dimensional metric of the torus looks a little bit more complicated. It's off-diagonal. It leads to this particular complex structure. And again, I display the monodromy what is happening when I go around the base in the x3 direction. So this looks fairly standard, but something more interesting is happening if I do another T-duality in x2. And now for the first time I obtain a non-geometric space, which is called a T-fold with Q-flux. The T-fold has a non-trivial metric in the 1-2 directions and also a non-trivial B field in the 1-2 directions, given in terms of this function. So this function depends on x3. And now I again play the same game. I ask myself, what is happening if I go once around the base? And I see that the scalar parameter, which takes this form, undergoes now a non-trivial modular transformation, which basically also acts on the volume of the space in a non-trivial way. So this is indeed non-geometric space. It corresponds, does not correspond anymore to a standard diffeomorphism, but to a T-duality transformation. Finally, I have a three-dimensional space. I can do another T-duality in x3. This is a little bit more complicated and dangerous because now I do a T-duality in a direction on which the metric depends on. So this violates basically the Busher rules, but formally, or better even in double field theory, I can do it. And then I get a non-geometric space with R-flux. And here it is difficult or impossible to write down a metric and a B field which depends as a local function on the coordinates. Because I do a T-duality in this direction, I would get a non-local expression for the background fields. And this is part of the complication here. So this was my introduction about these spaces. And now I will like to come to the discussion about non-commutativity and non-associativity. Before I do the closed string case, let me remind you briefly to the open string story, because non-commutativity was already known for the open string about several years ago. Namely, it was known that the coordinates of open string endpoints are non-commutative if I have two-dimensional or higher dimensional branes with so-called two-form F-flux or also B-field. And then by worldsheet techniques, by worldsheet quantization, you can compute this commutator. And you see that the right-hand side is non-zero. It's given by a certain deformation theta, which depends on the flux in this particular way. And one also should maybe emphasize that the right-hand side is a constant here. And this is a very famous result which gave rise to non-commutative gauge theories by Seiberg and Witten, and also by Julius Wess and his collaborators. As an interesting remark, I would also add here that if you go to the T-dual picture, namely at a D1 brane at an angle, namely the intersecting branes, which I have mentioned already, then the torus becomes again commutative. So there is a certain ambiguity also in the geometry, namely in the sense what kind of T-dual picture one is precisely using. And the same thing essentially will also happen now also for the closed strings. Okay, so we considered now, switching back to closed strings, where non-commutativity was not yet known, I believe. We consider two different types of models, namely non-geometric backgrounds, first with so-called elliptic monodromy and non-constant fluxes. They can be described by, in terms of asymmetric orbifolds, the four orbifolds. This also relates nicely to previous work of Lewis and collaborators. But for kind of pedagogical reasons, so this was done in these papers, basically 2010, I think, for the first time. And but for pedagogic reasons, I would discuss this chain of four models, this chain of four models which are related by duality, by T-duality, which I have introduced before. Namely, to recall the flat torus with H-flux, the twisted torus with F-flux, the non-geometric space with Q-flux, and also the non-geometric space with R-flux. As we will see here, for these two types of geometric compactifications, there is everything is commutative. Here, the space, the torus upstairs will become non-commutative, and the deformation parameter is now the Q. And the winding number, and this is important in the third direction, will appear here. And finally, the R space is the one which will become non-associative, namely this double commutator will be non-zero. Okay, maybe I should not give all the technical details of how to derive this result. One important thing is that one cannot quantize the string at every order in the fluxes, because the B field is non-constant, or the metric is non-constant. Therefore, one has to set up a perturbation theory, and we did it linear order in the fluxes. What is, however, important that one always has one has to consider these so-called boundary or monodromy conditions, which tell you how the space is defined, and they are very important. And they give now rise to new closed string boundary conditions, because if you have a closed string, it can wind around the third direction, so it can have a certain winding number in the third direction. So you have this standard closed string boundary conditions, but I have told you before that also something with the other coordinates is going to happen if you wind around the base correction. And what is going to happen is that the coordinates or the dual coordinates will also be transformed into each other in case there's this H flux here, and in case we are considering configuration with non-trivial winding number. So for the H flux, it looks like this. By the way, this was also played a kind of important role in one of our papers with Lewis, where we considered also how coordinates get transformed into each other via T-duality transformation. So it's basically the same effect here. You can do it also for the F flux. And now you quantize the string with these boundary conditions. And for these two spaces, you will see that everything is commutative. So let's go to the non-geometric Q flux and play the same game. There are two consistency requirements. First is the requirement that this space is dual to geometric compactification. So you can use something which was also developed by people which are very well known here, namely by Enrique Alvarez and Luis Alvarez Gomez and Yolanda Lozano, namely the so-called canonical approach to T-duality, the worldsheet approach. Very importantly, again, you have to obey the closed string boundary conditions. And these are really now very non-trivial, because you see that the action on the base has a very non-trivial effect in the fiber, namely it exchanges coordinates with dual coordinates. So there's really a very non-trivial transformation which exchanges the normal space with the dual space. And I would call this similar to so-called Dirichlet-Neumann boundary conditions for the open string. So the monoid now mixes coordinates with dual coordinates. And this one can also see as a kind of a definition of a non-geometric compactification. Yes, that's fine. And the winding number is again important here. So if you do this, you push this program through, and then now indeed for the first time you see that the commutator of the two coordinates in the fiber become non-commutative. So there's this formula here. It goes again with the winding number. So it's dependent. If the winding number of the string in the base is 0, then of course the space upstairs in the fiber would be commutative. But for non-zero winding number, you have this. You can perform also the limit of sigma goes to sigma prime, and then you obtain this simple expression on the right-hand side of the commutator. So the non-commutativity of the torus coordinates is determined by the winding in the base direction. So this is a kind of new uncertainty relation. The uncertainty in the x1, x2 directions grows with the dual momentum in the third direction. So it means that we have to have non-local string with wind around the third direction. Finally, let me also very briefly mention the R flux. You can do another T-duality, as I've mentioned before, and this basically exchanges the dual momentum by the normal momentum. So now this relation looks like this. Now the ordinary momentum or momentum operator appears here on the right-hand side, and then you can continue to compute. You use the canonical commutation relation between x3 and p3. You see that the Jacobi identity is violated, and then you get precisely this nice non-associative algebra, which mathematicians also like very much. It is called a twisted Poisson structure, and these were discussed even by Roman Jakif several years in the context of the magnetic monopole. So I think hopefully the chairman gives me 2 more minutes, then I will be done. So I will be very quickly mention our recent work on Q and R brains. Al-Zaban showed you already the standard Neveu-Schwarz action, and as you know, one solution of it are Neveu-Schwarz 5 brains, which are the sources for H flux. So this is a nice Neveu-Schwarz 5 brain configuration. You can do one T-duality in one direction, and then you get a Kaluza-Klein monopole, which is the source of the geometric flux, of the F flux. So what is happening when we do more T-dualities? Then we expect some new brains, which are the sources for non-geometric fluxes, and this is precisely what is going to happen. So we can construct now a Q brane via T-duality, but I also like to mention that this Q brane can be also obtained in a rather different way, namely there's another action from double field theory which describes these non-geometric fluxes obtained by us during last year, basically. So there's a new configuration, and there's an associated so-called beta field, a bivector, and the Q flux is basically the derivative of the beta in one particular direction. But the upshot is that this brane now is so to say, the microscopic source for the Q fluxes. And finally, there's also an R brane. Now what one can do also, one can use intersecting configurations of these branes, so configuration 6-dimensional spaces which have various type of fluxes, and then you get flux backgrounds, particular flux backgrounds, which have a vibration structure, which have interesting boundary conditions. So let me show you just it's 1 more minute and I'm done. A few examples. You can start, for example, with the intersection of 4 Neveu-Schwarz 5 branes. This gives rise to a particular superpotential. You can T-dualize it, then you have the intersection of 4 Kaluza-Klein monopoles. This gives a twisted torus with 4 particular F fluxes, the Iwasawa manifold. But now you can continue. You can T-dualize further, and then you get a space which has 4 Q fluxes. So these dots somehow indicate, do not discuss the details, how the Q fluxes are related. And one can compute the superpotentials. You get similar formulas also as in the paper by Luis Ibanez et al. And finally, you can even get configurations with R fluxes and also configurations which have mixed type of fluxes. So this we studied in some detail. We wrote down the 4-dimensional effective superpotential and showed that using these intersecting Q and R and F branes, one get very nice flux compactifications with the moduli stabilized. So, okay, this was now the present, and very quickly to the future. What is the outlook and open questions? I've tried to argue that these mixed closed-ring boundary conditions lead to closed-ring non-commutativity. We want to investigate this more. The phase space of double geometry, also the relation to generalized or double geometry in the generalization or the relation to non-associativity with respect to the generalized diffeomorphisms. Of course, there's a very interesting question whether one can now formulate also a non-commutative or even non-associative theory of gravity. And since we have now non-associative objects, one has also to notion the concepts of operators for the non-associative geometry. So the question is how to represent this algebra. So I just finish with wishing you, Louis, again, I know your birthday is not today, it was already last year, I believe, but nevertheless, I'd like to wish you a happy birthday and all the best to you and your family.